In this video, we want to look at our last section, and that is doing hypothesis test for the variance, which is sigma squared, and the standard deviation, which is sigma. So as we do this, you want to be careful that you pay attention of, are they giving you the variance, sigma squared, in the problem, or are they giving you the standard deviation, which is sigma? And just try to keep that straight. This is also different than any of the other ones we've looked at so far because this is not on our calculator. We're going to have to go back and use our chi-squared chart to be able to find our critical values from our chi-squared chart. So this is a little bit different than the ones that we have looked at previously. Now let me say there is something on your calculator that if you go to test and you go down to the bottom, there is a chi-squared test. This is something completely different. I will just show you. If you click on it, it asks for observed and expected and deals with matrices, something completely different. We will look at that later this year, but that is not going to help us with what we are doing here today. So our chi-squared test, the first thing we need to do is we need to find our critical values. And finding these critical values is very similar as the same chart that we used when we did finding the critical values before. If you remember, here is a copy of the chart. It's going to see a part of it I'm going to use here in the video, hopefully on your formula sheet, or if you just Google chi-squared chart online, you will find this kind of formula sheet. So let's talk about how we use this. So when we do this, we have three possibilities. We have a right-tailed, a left-tailed, or a two-tailed test. And if you remember, if we think about this is all based on our H sub A. So if our H sub A was, let's say sigma is greater than 4, that's going to be a right-tailed test. If our H sub A was sigma is less than 4, that's a left-tailed test. And if our H sub A was sigma does not equal 4, that is a two-tailed test. The other thing we got to remember is that this chart that we use for our chi-square distribution always is the area to the right. So if it's a right-tailed test and we have sigma, we're good. We have alpha, we're good. We just use alpha. If it's a left-tailed test, we're going to use alpha minus 1 because it's the area to the right. And if we're using a two-tailed test, what we need to do is we use half of alpha for the 1, and then the other one we want to use this way, which would be 1 minus 1/2 alpha for the other one to get both our left and our right critical value. Now, what we're going to do to do this test is we're going to find that critical value in our chart. And that critical value is going to be based on whether it's a right, left, or two-tailed, excuse me, and what our alpha is. So let's look at an example. Find the critical chi-squared value for a left-tailed test when alpha is 0.01 and n is 11. Now, the first thing to remember is when you're doing this, we need degrees of freedom for chi-squared. So first off, we got to go to our degrees of freedom, so we're going to go to 10. So if you have your chart, you're going to be looking at the line of 10. Secondly, it's the area to the right, so we have to take 0.01 minus 1 to get 0.99. So if we think about our chart here, the area to the right is going to be our 0.99. So we're going to look up 0.99 in the chart. So before we show the answer, let's go over here. So we are in the 10. So we go across here is our 10. Then we are in 0.99. So then we come down 0.99, and our value is 2.558 is our value of our chi-squared critical value, 2.588. And when we write this, this is our critical point, is our chi-squared 0 is our 2.558. Just so we understand the notation here, this 0 is what you get from the chart, and it makes that shaded area. Let's try another one. Let's find the critical value for chi-squared for a right-tailed test of 26 with 0.1. So degrees of freedom is 25. The right is the critical, so we can just look up 0.1 in our chart. So if we go back to our chart, our degrees of freedom is 25. Now I need to scroll down. So our alpha is 0.1. So we're going down this chart. And if we go down to 25, we get our value right there, which you can see is our value of 34.382. Okay, scroll down here. 34.382 is at 25. The final one is if we have a two-tailed test. If we have a two-tailed test, what we have to do is we still have our degrees of freedom. That doesn't change. But what we have to do differently is we need to find two tails. We need to find one for each. So we're going to find our two values, which are 0.025, which is this left part, 0.975, which is the right. So we look up those two numbers in our chart, and we get 0.218 and 17.35. If we go back to our chart, our degrees of freedom was 8. So if we look at our line of 8, and we have our 0.025, which is 17.53, and then our 0.975 is 2.18. Remember, these always add up to 1. So once we find our values, what do we do next? Now, if you'd like some extra practice, there are 3 problems here on the notes, which you can pause the video if you want to try these to see if you can find these on your chart correctly. And then once you restart the video, I will write down what the answers are, and you can see if you can get it right. All right, coming back, it's a right-tailed test, so we can use the 0.01 directly. We don't need to do anything. Degrees of freedom is 17, so you would get 33.409. If it is a two-tailed test when n is 51, so our degrees of freedom is 50, it is 0.01, so you'd have 0.005 is your one value, and then 0.995 is your other. So your two values here are 27.991, and your other value, I guess I should label these left and right, is going to be 79.490. And our last one is a left-tailed. So because it's a left-tailed, you have to subtract, and in your chart, you want to think of 0.95. And it's 30, so my degrees of freedom is 29. So if I look this up, I get 17.709. So how do we now do that we have our chi-squared value? So what you want to think about, if this is a left-tailed test, I'm going to kind of draw the graph here. We want to roughly draw the graph like this. And if it is 17, it's a left-tailed test. So this right here is 17.709, and we get this shaded region right here. And then what we're going to do is we are going to calculate chi-squared by using this formula. N minus 1 S squared over sigma squared. Once we have that chi-squared value, we're going to compare that value to our chart. If our chi-squared value is, let's say, 16 over here, since that is in this shaded area, that would be a reject, H sub O. If my chi-squared value was over here, chi-squared equaled, let's say, 18, this isn't quite the scale, this would be fail to reject. So what we are going to do is find our chi-squared value in our chart and then kind of shade it if it's a left, right, or two-tail like we did back here. We then are going to find our chi-squared value from our problem right here and then decide if we reject or fail to reject based on where that is at. So let's look at an example. So here are 4 different chi-squareds that come from problems. Here is a right-tailed test where our chi-squared 0 is 10.645. So if I look at this, 10.065, that is going to be over here. It's going to be to the left. So since it's not in the blue, that is a fail to reject. 10.075 is also over there. That is a fail to reject. 10.585 is also over here. It's less than 0.645, so that is a fail to reject. 10.745 is over here. It is past chi-squared 0, so that is in the blue, so that is a reject H sub O. So that is how we're going to determine if we reject or fail to reject H sub O. So let's look at an example. A dairy processing company claims that the variance, that's sigma squared, for the amount of fat in a whole milk processed by a company is no more than 0.25. You suspect this is wrong. You find a random sample of 41 milk containers that have a variance of 0.27. At the alpha of 0.05, is there enough evidence to reject the company's claim? Assume the population is normally distributed. Step number 1 is we need to write our H sub O and our H sub A. In this case, our H sub O was sigma squared is less than or equal to 0.25, and sigma squared is greater than 0.25. If you write that down, if you don't have the problems printed off, we can go back here and you can see it's no more than 0.25, which is our H sub O and H sub A. Next, we need to find our chi-squared. So we're going to put it into that formula. N minus 1 S squared over sigma squared. So 41 minus 1 over 0.27, 0.25. Notice the squares are gone because they give us the variance. The next thing, this is a right-tailed test. Our alpha is 0.05. Our degrees of freedom is 40. So we have to go to our chart to find that value, and that value is 55.758. That came from our chart. Our chi-squared value that we got up here from our formula is 43.2. That is not in the shaded region, so that means we fail to reject. And then if we write our sentence, we can say there is not enough evidence to support the claim that the variance of the amount of fat in the company is more than 0.25. So you can see the reject, the fail to reject, the H sub O, the H sub A, all of that, the sentence is very similar to our z-test and our t-test and our p-test. The difference with the chi-squared test is we have to get our chi-squared value from this formula and our critical value from our chart to determine whether or not we reject or fail to reject. Let's look at one more. A company claims a standard deviation of the lengths of time it takes incoming phone calls to be transferred to the correct office is less than 1.4 minutes. A random sample of 25 incoming calls has a standard deviation of 1.1. Alpha is 0.1. Is there enough evidence to support the company's claim? So once again, notice this is the standard deviation. So that's just sigma. That's not squared. So when we write our H sub O and our H sub A, we have sigma. Our previous example, we had sigma squared. So you have to kind of change it based on what the problem is. We now find our chi-squared. Notice our 1.1 and our 1.4 have to be squared. They're the standard deviation. If they're the variance, they're already squared. We have a left-tailed test. So if we have a left-tailed test, we have to find our value in our chart, okay? And our value in our chart is 15.659. our chi-squared was 14.186, so you can see it is over here in the blue. Since it's in the blue, we reject H sub O. So now our sentence will be, there is enough evidence to support the claim that the standard deviation for the lengths of times of the incoming call to be transferred is less than 1.4. All right, you are ready for the homework over 7.5. Once again, once you have finished the homework, you can take a picture and upload it to Google Classroom.